gases in the blood. And so our third objective is to describe the transport of our different gases, which are oxygen and CO2, in the blood, which again is really just carrying on the conversation from the last packet. In the last packet, we just described why we need to do what we're going to do here, why we need this hemoglobin to shuttle oxygen around based upon the different solubility of oxygen and kind of the lack of solubility of oxygen in the blood. And then also based upon the partial pressure gradients that we need. And so in this packet, we'll speak about how hemoglobin plays a crucial role in moving that oxygen around our system, okay? And how that oxygen interacts with that hemoglobin. And so this brings us to speaking about oxygen and how it is loaded and offloaded onto hemoglobin and kind of the why of that. So we described previously that only 1.5% of arterial blood oxygen is actually dissolved in our plasma. And that was really because oxygen does not dissolve or solubilize very well in blood. And so the remaining oxygen that is transported in our system, in our blood, is done so bound onto hemoglobin, okay? If we were to circulate oxygen only dissolved in our blood, we would have to increase our cardiac output about 5 to 10 times what it currently is in order to adequately oxygenate our tissues. And so there's very, very little oxygen being circulated in its dissolved form, and most of that oxygen is being circulated bound to hemoglobin. And so what that gives us is hemoglobin, which can be bound to oxygen, not irreversibly, but reversibly. So we can bind oxygen to hemoglobin, and on the left, this is called deoxyhemoglobin. And we've got these double-headed arrows, which indicate that this is a bidirectional reaction. And on the right here, we have oxyhemoglobin. So when hemoglobin has oxygen bound onto it, it's oxyhemoglobin. And when it doesn't have oxygen bound, it is deoxyhemoglobin. And so we can drive this reaction in either direction, depending on the amount of oxygen that is present. So if we have a lot of oxygen present, we're going to drive the reaction to the left. If we have a little bit of oxygen present, we're going to drive the reaction to the right, okay? Looking at our images here on the right, we can basically see that oxygen is going to cross the alveolus, cross that respiratory membrane, bind on to our hemoglobin here. And it's not going to bind too tightly that it cannot dissociate when we get down to the level of the tissue. So it's really important to understand that this is a reversible binding. Unlike what we'll speak about, carbon monoxide, which can bind onto hemoglobin, but it does so irreversibly. And then it's going to circulate in the blood. And when we get down to the level of the tissues, oxygen will dissociate off of hemoglobin and cross the capillary beds and into our tissues, okay? Now, we want to point out that there has to be a change in hemoglobin such that it wants to bind oxygen or grab that oxygen at the alveolus, and then it wants to let go or not be attracted to that oxygen when we get down to the level of the respiring tissues. And that's what we'll spend the rest of this packet speaking about. What is the change that happens on hemoglobin to be tightly attracted to oxygen within the alveolar capillaries, and then not attracted to oxygen down at the level of our systemic capillaries, okay? So this brings us to speaking about the saturation of hemoglobin. So we know that hemoglobin can bind up to 4 oxygen molecules, and when it does so, we can say that it is fully saturated or 100% saturated. And the binding is going to follow the law of mass action. In other words, if we have more oxygen, it's going to bind more hemoglobin and drive our reaction towards products, right? That oxyhemoglobin. If we have more oxyhemoglobin, it's going to drive our reaction in the opposite direction, which is towards our reactants. And so this is what we mean by the law of mass action. If we've got more substrate or more reactants present, we're going to drive the reaction towards product. If we have more product present, we're going to drive the reaction towards substrate or towards reactants, okay? And on that basis, we could think about saturation as being how many oxygen molecules are bound onto that hemoglobin of the 4 that it can ultimately bind. So if it can bind 4 oxygen, and just to remind ourselves of the structure of hemoglobin here, we've got our 4 subunits, right, 2 alpha, 2 beta. In the center, we've got our 4 heme groups. And the iron that's contained in these heme groups is where that oxygen will ultimately bind. And so we can bind 4 of those oxygen molecules per hemoglobin. And so we can think about hemoglobin as being fully saturated when it has 4 oxygen bound. And then we'll talk about it being partially saturated, right? Not necessarily being unsaturated, but unsaturated would mean that it has no oxygens bound. But in actuality, in our physiology, hemoglobin is never unsaturated. It's either fully saturated or partially saturated. And we'll talk about why that happens in a little bit. But basically, we can load oxygen into the lungs when it is in its partial saturated state, and then it goes to its fully saturated state. And then we can offload that oxygen down at the level of our capillaries and our respiring tissues when it goes from its fully saturated form back to its partially saturated form, okay? And so for simplicity's sake, we're representing this here as having no oxygens bound, but I'll talk about why in a little bit. It actually does always have at least 3 oxygens bound onto that hemoglobin. Okay. So let's speak about how this oxygen binds to this hemoglobin and our different rates of saturation. So when we have 100% saturation, one hemoglobin can carry 1.34 milliliters of oxygen. Now, in a normal, healthy adult with no anemia, no pathology, we typically have about 2 to 17 grams per deciliter in terms of our normal standard hemoglobin levels. And so if we were to multiply these 2 factors, this would give us a rate of about 200 milliliters of oxygen per liter of blood that is circulating in our vasculature, okay? That is described as the oxygen carrying capacity of hemoglobin in our blood, okay? So we multiply the oxygen saturation rate and how much oxygen is being supplied by the amount of hemoglobin that is typically in our blood, and that gives us our oxygen carrying capacity. Now, if you think about our arterial blood, this has hemoglobin in its fully saturated state, and it's not actually 100% saturated. It's actually about 98.5% saturated, and that is kind of the maximum saturation that we see in the state of hemoglobin in our blood. In our venous blood, again, we see about 75% saturation. In other words, hemoglobin is never fully saturated at 100. It's never completely empty at 0, but it actually fluctuates between 75% saturation and about 98.5% saturation as we go from our venous blood, where it has less oxygen, to our arterial blood, where we see more of those hemoglobin binding more oxygen, okay? And so just looking at what that looks like here on the right, we see most of our hemoglobins fully saturated, in other words, having 4 oxygen molecules bound to those heme groups. And we do see one that does not have 4 oxygen, indicating that it's not 100%, maximum capacity. It's just about 98.5 or so. And then in our venous blood, we see that all of the hemoglobins are not completely empty. Instead, they just have lost 1 of their oxygen molecules, and they have about 3 oxygens bound to that hemoglobin, okay? And if we can think about the partial pressures of these, the partial pressure of the gases in the arterial blood versus the partial pressure of the gas in the mixed venous blood. So in our arterial blood, when hemoglobin is at 98.5% saturation, we see the highest partial pressure in our vasculature. It's about 100 millimeters of mercury, okay? And this is freshly oxygenated blood that is moving through the arterial side of our vasculature. And we can compare that to the state of hemoglobin when it is 75% saturated. This reflects a partial pressure of oxygen of 40 millimeters of mercury, which is our lowest recording for the partial pressure of oxygen, which is found in our mixed venous blood. In other words, that deoxygenated blood that's going back to the right side of the heart. Okay. And if we think about how this binding happens, so oxygen and hemoglobin exhibit what's called cooperative binding. And so we're comparing here the partial pressure change of oxygen. So we go from 0 partial pressure on the left all the way to 100 partial pressure. And in terms of our physiology, it's about 40 millimeters of mercury in our systemic veins, which is the lowest partial pressure of oxygen in our physiology, all the way up to 100 millimeters of mercury in our systemic arteries, which is the highest partial pressure of oxygen in our vasculature, okay? And we're comparing that to the percent of oxygen saturation. In other words, how many oxygens are bound to that hemoglobin. Okay, if we have 1 oxygen bound, that's 25% saturation. If we have 2 oxygens bound, that's 50% saturation. If we have 3 oxygens bound, that's 75% saturation. If we have 4 oxygens bound, that is 100% saturation, okay? And so basically in our system, we only go from 75% saturation, which is 3 oxygens bound, to 100% saturation, which is 4 oxygen bound. And so what this really means is that our deoxygenated blood always has 3 oxygens bound onto it. And the exchange that takes place at the level of our systemic capillaries only takes that 4th oxygen. And then the exchange that happens in our alveoli only replaces that additional 4th oxygen. And so moving through our vasculature, only this 4th oxygen binding is influenced by the gas exchange that we see at the level of our alveoli or the level of our systemic capillaries, okay? I do want to point out one more thing here. This cooperative binding that we see for oxygen is really a reflection of the affiliation of oxygen to hemoglobin. And what that means is when the first oxygen binds, so when that first oxygen binds to our hemoglobin, the attraction between hemoglobin and oxygen really increases such that the distal part of the curve is more linear, okay? Or it's not more linear, but more steep. Okay, and so what that means is that after that first oxygen binds and we're at 25% oxygen saturation, the attraction now increases such that the 2nd, 3rd, and 4th oxygen are going to bind with much more ease than that first oxygen did. All right, and that was what we mean by that cooperative binding. And this is the reason why oxygen always has hemoglobin always has those 3 oxygen molecules bound onto it so that it can facilitate the ease of binding that 4th oxygen and facilitate the ease of gas exchange in terms of oxygen being loaded and offloaded into our respiring tissues or being picked up at the level of the alveoli.